Assalamualaikum warahmatullahi wabarakatuh. Today I would like to present my progress report for a title of Synthesis, Characterizations and Kinetic Modeling of Metal Oxide supported on extracted alumina catalyst in the co-pyrolysis of cotton fabric waste and plastic to produce bio-oil. My name is Nur Alwani binti Ali Bashah. So currently I'm in semester 4. My supervisor is IR Dr. Wan Zuraida Khamis and co-supervised by Dr. Muhammad Zairuddin Amri, Associate Professor IR Dr. Siti Shawala Idris, and Associate Professor Dr. Muhammad Anwar Kamaruddin. Here is the presentation outline. There are 9 items that will be discussed in this presentation. I will start the presentation with introductions and will discuss in detail on current research progress, and will end this presentation with the planning for the next semester. Currently, the emissions of greenhouse gas has become a global issue due to rapid utilization of fossil energy such as oil, coal, and also natural gas. Recently, explorations on renewable energy from biomass resources has attracted global attention due to biomass is zero net carbon, it is abundant, great economic potential, and it is easily to be utilized as direct combustion as well as suitable to be adapted into current technology, which is pyrolysis technology. There are various types of feedstock to be used as biomass resources. It includes plant, woods, or waste. Statistics shows that there are increment of textile global market whereby could generate more waste. About 195,000 tons per year of fabric waste was dumped in the landfill. Statistics in Malaysia also shows that about 7 to 12% of plastic waste has been dumped in landfill. This two-waste material is seen to have potential to be used as feedstock because textile rich in cellulose and plastic is rich in hydrocarbon. The combination of these two materials as feedstock perhaps enhance the production of hydrocarbons in pyrolysis product. The co-pyrolysis can be conducted by adding the catalyst. Additions of the catalyst will enhance the product yield and selectivity towards hydrocarbons and aromatic. There are various types of catalysts available, such as acid catalyst and also basic catalyst. Acid catalyst usually increase the yield and also aromatic of hydrocarbon, and basic catalyst usually used to reduce acidity of bio-oil. Recently, the researcher also explored on the catalyst generated from waste, which contains, as we know that the waste which contains precious active metals such as aluminum, ferrum, potassium, sodium, and also calcium. Recent research is developing mesoporous catalysts, bimetal catalysts, and also adopting industrial solid waste as catalyst. The transition metals is highly efficient and cost-effective catalyst. It is usually used as additive of active metal with other catalysts or support. By modifying catalysts, modifying the amount of the metal in the catalyst, it could modify physicochemical properties that prone to upgrade into hydrocarbons compound by its preparation method. Thus, S-flow catalysts derived from industrial sludge waste with additions of promoter, which is transition metal, will be discussed further in this study. In this study, we will focus on the utilization of biomass as renewable energy and alternative into the conventional fuel. The issues on the utilization biomass is the low quality bio-oil produced from pyrolysis process due to high oxygen content in the bio-oil. It is also to cater on the environmental concern on greenhouse gas emission from rapid utilization of fossil fuel energy, as well as gas, water, and land contamination from landfill activities. The solution proposed to encounter these issues, the first one is upgrading technique using pyrolysis with hydrogen donor material and utilization a catalyst in pyrolysis process. The second is to use waste material as feedstock, such as textile and plastic, and also waste material to develop a catalyst. Some of the contributions outlined after fulfilling this project. The first one is production of sustainable bio-oil for biomass, which is using cotton fabric waste and plastic waste, which is using polypropylene waste. The second one is development of the catalyst from industrial solid waste. And the third one is it will support nation government goals in addressing renewable energy and sustainability development outlined in SDG 2023 and also SPB 2030. There are 4 objectives outlined for this study, and also each of the objectives is outlined the scope of the study. Here in this presentation, I would like to focus on the first objective, which is to synthesize and characterize several series of heterogeneous catalysts comprises of metal oxide, chromium, and NEA, which as outline formulation by variations in synthesis condition, maturation, calcination temperature, or also calcination time. In this slide, it shows the methodology upon completion of the study. The first objective is, at this stage, synthesis and modified catalyst by varying metal ratio, calcination temperature, and calcination time. The best catalyst from all these 3 combinations synthesis effect will be used further in evaluating the effect of process parameter to achieve objective number 2. In this slide, we will discuss on the catalyst characterization, which is effect of calcination temperature. As we can see from the BET analysis, the textural property shows that at higher calcination temperature, it tends to produce more porous material and develop more pores. Okay, this one is supported by the SEM image, whereby we can see from 15 CE 705, the image shows that there are many rocks appear on the surface of the catalyst. Figure 2b shows that the acidity of the catalyst also has been modified by changing the calcination temperature. As we can see that most of the catalyst is fall under acidic, medium and strong acidic region. However, at the highest calcination temperature of 800 degrees C, it reduced the acidity of the catalyst and fall into weak acidic region. And we can see over here from figure 2D, the stability of the catalyst is also modified when the temperature of calcination temperature is reduced. So we can see the catalyst is more hygroscopic when we reduce the calcination temperature. This is supported by FDAR result, whereby we can see that at 400 degrees C of calcination temperature, it appears to have OH stretching and bending, as we can observe at 3000 to 3600 wavelength, and also 1600 to 1700 IR wavelength on the surface of the metal. So now let's look on the activity of the catalyst at various calcination temperature. So from figure 3a, we can see that the yield of bio-oil is achieved at the maximum when the pyrolysis process is conducted with the presence of 15 CE for 600 degrees C and 5 hours. So what we can see here, the trend of the we can see increase in trend when we increase the calcination temperature. However, after 600 degrees C, the yield is sustained at about 35%. So it also can be seen the product distribution is also altered from different calcination temperature of the catalyst. Increasing the calcination temperature, it would increase the formations of the hydrocarbon while decreasing the formations of alcohol. As we can see, the agreement between all the catalysts, it produces lower acid, and also it could convert most of the sugar derived from the feedstock. However, we can see that at the maximum yield, it produces about 40% of the hydrocarbon and 34% of the alcohol, and it also produces high phenolic and also high purines, and it produces high carbonyl product. Okay, so from the gases product distribution, we can conclude that most of the reactions happen is following decarboxylations and decarbonylations as it become a main pathway of catalytic reaction. Okay, and also we can observe that hydrogen and methane gases will slightly increase when the catalyst, when the process is run with high calcination temperature of the catalyst. So it's suggesting on it might be following the hydrogenation pathway, and also possible to have cleavage of CC or CH bonds at the higher temperature. So the FTIR spectrum suggests the presence of the alcohol, alkaline, alkene, carbonyls, and also phenols. So now let's look into the effect of calcination time. Figure 4a shows the BAT isotherm, whereby the low nitrogen absorptions and desorptions into the catalyst is observed. The pore distribution shows that most of the pores fall at micropore range, which is less than 6 nanometer, when calcined at different calcination time. It also suggested a dense particle. Although some distribution is seen at pore size more than 6 nanometer, it could be rock surface or an interparticle spacing between chromium and EA. The surface area and pore volume shows lower than 15 CE 605 catalyst. For chemical properties, we can see that all the catalysts possess similar trend, which is fall under medium and strong acidic region. And when we look at on the Fassan image, we can see a regular hexagonal shape for all catalysts dispersed on EA. However, the image shows that the chromium tends to agglomerate at longest calcination time, which is 6 hours. So this figure 4D display the catalyst stability, which the catalyst show more hygroscopic at longest calcination time than others. And the FTIR spectrum shows that most of the catalysts display a similar wavelength, okay, whereby we can see at 400 to 800 wavelength, which suggests metal oxide interaction. Some distinct IR band for 15CE606, whereby we can see clearly on the OH stretching and bending at 3000 region and 1600 region, which assigned to vibration of hydroxyl attached on the surface. It probably assigned to the vibration of the hydroxyl attached to the surface of the metal. Okay, let's discuss on the effect of calcination time on catalytic activity. As we can see from this figure, the yield is consistent for each of the catalysts when changing the calcination time. However, we can see that the 15CE605 poses the catalytic effect differently from other type of catalysts. As we can see that the hydrocarbon is slightly produced about the same for all the catalysts. Same goes to alcohol. Okay. However, it produces large carbonyl by increasing trend when increase the calcination time. Okay. So we can see from the figure 5C, most of the catalysts shows the main reaction involved via decarboxylation and decarbonylation. However, 15CE604 display low formation of CO and CO2 gas, suggests the reaction follow other pathway. It might be a cleavage of CC or CH bond. As we can see also, the product distribution for 4 hours of calcination time produce higher in hydrocarbon, and also 6 hours is produced the highest of hydrocarbon. The FTIR spectrum suggests the presence of alcohol, alkene, carbonyls, and also phenol. As we can see, most of the IR band follow the same pattern, except for the intensity or shifted of the wavelength. However, it's still within the range of the product. So this is the time chart for my current study. So as we can see from here, for the first objective, it's already completed. So moving forward to the second objective, which is catalytic co-paralysis of CFW and PPW by varying the effect of process parameter. Publication status and thesis writing. So I'm in the middle of writing my first paper, which is after the completion of the first objective, and currently this thesis writing status is about 40%. And the last but not least is my planning for the next semester. The first one is we'll continue to study on the effect of operating parameter, which is reaction temperature, profit ratio, catalyst loading, and also reaction time, and analyze the product characterization. So this one is estimated completions in September 2023. And the second one is conducting a reusability and regeneration study, which estimated to be completed by October 2023. That's all for my presentation. Thank you.